Okay, so we're still trying to make function, right? We're modeling functions. So we're using our calculator and we're doing linear regressions and we're doing quadratic regressions and we're seeing how well they fit our data. Okay, so today is all about how well does it fit. So here we have some data about newborn babies. It says newborn, the weight of a newborn baby can be modeled by a linear function for the first 4 months after birth, right? Only for our first 4 months. So that would be our domain. We're only talking about the first 4 months. And the range would be the weight of the different babies. So first, let's plot these couple of values on our table and see what kind of a graph we get. So there are our points. Now let's answer some questions. Based on the graph, what type of function would best fit? Well, we're told it's a linear model, so this would be a linear function that we're going to be checking in our calculator. Okay, so then what is the regression equation? This is where we go to our calculator and we figure out what our linear regression line is, our y equals mx plus b. So there is your linear regression, 0.8x, that would be the slope, right? The slope of our line, and then 3.34 would be your y-intercept. Okay, so no, the y-intercept is not the same as this because our equation doesn't start there. It's the line of best fit. Okay, so what it says, what is the r squared value, right? This is also given to you in your calculator. My calculator says 0.9888. Okay, so this is my r squared value, and that tells you how well your data fits this equation. Okay, that's what this value means. So your r squared is a statistical, not right, this is a statistical thing that statistics calculates for you. Okay, and that tells you how well your equation fits your data. Okay, because it's not going to be a perfect fit. So every one of these y values, right, so maybe let me draw the equation in here. Maybe this was, right, 3.34 is in here. Maybe this was the equation, right, of your line or something. Maybe, right? So notice how not all of these points are exactly on the line, right? They're a little bit off, a little bit above, a little bit below. And that's okay, because this is a calculated equation. Right, so what we're going to talk about today is this distance, the distance in between your equation and the actual value. These little differences here, these are called your residuals. It's the difference in between the actual data point and the approximated data point using your equation for that same time period. Okay, so there should always be a little bit of difference, sometimes above, sometimes below, depending on how well your equation matches up with your data. Okay, so this is what we're going to talk about today is the residuals. What is left over in between the actual data points and what's calculated by your regression line. Residuals, the difference in between your points. And that's what this little paragraph says right here. Okay? When you create a model, you use the model to predict values for the given dependent variables, right? They're just the predicted. The actual experimental values may be different, especially far off into the future, right? We found that off in previous videos that is only good for the certain time frame, the equation that we model. Okay, so this is how we do a residual. The actual output value, this is your data point. Okay, this comes from your data in your table that you have gathered. Minus the predicted output value, this comes from your equation model. So if you do that subtraction, you can get positives and negatives. Okay, and that's perfectly okay to get a negative number. That means the data point was below the estimated point from your equation. Okay, so we can use that residual to check to see if our model was any good. Okay, is our model any good? So if a model is appropriate, the residual plot should appear random. Okay, not a specific pattern. It shouldn't look linear. It shouldn't look like a quadratic. It shouldn't look exponential. It should look random, some above, some below, right? So, I mean, it can be up and down, back and forth, randomized. Okay, if you can see a pattern, then it was not appropriate. And we'll look at some examples of that here in a little bit. So let's look at a couple of examples here. So we have, from example 1, when the baby is 3 weeks old. So our data says at 3 weeks, our baby is 5.8 kilograms. That's our actual value from your table. So for our predicted value, we're going to use 0.8 times 3 plus, I believe it was 3.34. Right? That was the equation that we got right here, our regression equation based upon all of the data. 0.8x, or 0.8 per month, times 3.34. So let's plug this into our calculator and see what we get. 5.74. Okay, so we have the actual value from our data of a 3-month-old baby, and we've calculated it at approximately 5.74. So if we do our actual minus the calculated, right, 0.06. So the interpretation is it's pretty good, right? It's only 6 1/100ths of a kilogram apart from where it's supposed to be. Okay, so let me show you what this looks like in your calculator for this data up here. Here's a picture of my calculator. So here was your M when we did our linear regression. Here was your B value. There's your R squared. Now see, this says resid. This is the residual screen. So your calculator will calculate your residuals for you. And look at all these numbers. Okay, these are your actual residuals. So the calculated minus the one from the data, right? Negative 0.14. The calculated minus the one from the data, 0.06. 0.16, 0.06, negative 0.14. Okay, so the calculator will, if you put your, I don't know what they call it, the little arrow over that box, all of these numbers up here are your residuals that you get. Okay, so in fact, we're going to do something with this in a second when we flip over to the other side of our worksheets. So here's the back side of the worksheet, and at first it has this plot here. We're going to plot each of these residuals from your calculator. Your 0, negative 0.14, your 0.06, your 0.16, your 0.06, and your negative 0.14. We're going to plot those here, right? So the residuals come from your calculator when you hover over the box next to resid. Okay, we're going to plot those. So let's answer some questions. What do you notice about the residual plots? Right, there looks like there's some symmetry here, but what kind of a algebraic graph is that? It's like a concave down parabola. So there's a pattern here, right? It looks like there's a pattern giving us a concave down parabola, which is kind of strange that that data, the residuals, would do this. So according to our box, was this regression equation a good fit? No. We would have to say no, because there's a pattern. There's a pattern to the residuals.
So what's the difference between this question and the interpretation of the same question?
So here is the takeaway. You need random residuals. Okay, your independent variables should describe the relationship so thoroughly that only random errors remain. Okay, not a pattern of errors. Non-random patterns in your residuals signify that your variables are missing something. Right? It means that your equation isn't a very good equation used to predict something in the future if your residuals give you a pattern. Okay? So here's an example looking at these three equations. Which model is most appropriate for the data? Is it this one that has this nice looking swoosh looking thing? This one that looks almost cubic? Or is it this one that goes up and down and back and forth? The answer is this one. Because the residuals, right, it says this is a residual model, is random. They do not form a pattern. If your residual plots form a pattern, then you do not have a very good model for your data. Okay? The next one, an exponential regression was used to model a data set. The residual plot for the exponential, right? So you need to read the words residual plots. That is a key, right? Because this does not look like an exponential regression equation. The residual plot, we want this to be random. Which of the following best conclusion about the appropriateness of the exponential regression model based on the corresponding residuals? Right? It's appropriateness of the model based on the residuals. So the model is not appropriate. What would you say? First of all, yes or no? Yes. This is going to be a yes one. So anything that says not is not going to be a correct answer because this is a pretty good residual plot, right? It's random. There's some above, there's some below. It goes back and forth and back and forth and back and forth. So is it C? Is it yes because they show no pattern, or is it yes because they do show a pattern? C, they show no pattern. Okay, so whenever we do a regression model, okay, look at the residuals. What you want to see on a residual plot is no pattern being formed.